All right, so welcome back. So we are in 1.4, still dealing with limits, and the two new topics, the topics that we want to cover is the idea of continuity and the idea of one-sided limits. Now, the good news is one-sided limits are going to be really easy for you to grasp as long as you were able to grasp two-sided limits, which is the limits that we've been doing in the previous videos. But let's start. So how do we describe a graph that is continuous? Well, I do like the way in elementary school they would have said that a graph is continuous if you can draw it without ever lifting your pen or pencil. And I like that. It's a little bit too informal for mathematics, but it does demonstrate what it is that we're talking about, right? So now, as you progressed, say, out of elementary school into middle school and high school, they would have done a little bit better than just saying if you can draw it without lifting your pen. And they may have said something to the nature of a graph is continuous if there's no holes, no jumps, something like that, right? Now, it's in calculus that we're able to formalize some things. So, for example, and you'll have to forgive, I know that these are handwritten notes. I did not know that I would be teaching this course online this summer. So a lot of my materials are at the college. So you're gonna have to go with some of my notes here. So let's try to formalize what we mean by continuity. Let's start with just at a point. So at a single point, right? So here's some graph, and if we're just focused on some single point, and to say that there's continuity, it's continuous, a graph is continuous at a single point. So let me start by let me just make up a random curve here. So here's some point C, and we are trying to talk about continuity at this point that we're looking at right now. So what does it mean to be continuous at some point? Well, first, f of c is defined. Now, what does that mean? F of c is defined. Well, that would mean that whatever this x value is that we're calling c, when you plug it into your function, what you get out is f of c. In other words, this is a more formal way of just making the statement no hole in the graph, right? Because if there was a hole here, then you could not draw this without lifting your marker, right? Okay. Well, what about the limit as x approaches c of f of x exists? So how do we interpret that? So what that would mean is that as x approaches c from the left side, your graph is approaching this y value. As x approaches c from the right side, your graph is approaching this value. And in order to say that the limit exists, that means they have to be approaching the same number from both sides, right? So this is a more formal way of saying that there's no jumps in the graph, right? No breaks. So, for example, if your graph was approaching this number from the left, but it was approaching this number from the right, well, you couldn't draw that without lifting your pen, right? I've mixed pencil, pen, marker. Next is crayon. Ready? The last bit is you actually have to have both, right? You can, in other words, remember that limits can exist when there's holes in the graphs, but continuity cannot, right? You can have, the limit must exist, and what they're saying here, the limit of f of x as x approaches c actually does have to equal f of c. So when you take c and plug it in here, you would get f of c, and f of c has to be the same as the limit. That's a more formal way of thinking about continuity than just no holes, no breaks, can lift it without draw it without lifting your marker. Well, we've discussed continuity at a point, but what about discontinuity, types of discontinuity at a point? So the types of discontinuity that we are interested in is that of what we call removable or non-removable. Let me see if I can make sense of what I'm trying to say here. So let me go up here to this graph, and now let me pretend that there's a hole there. So let's start with a removable. What do we mean when we say a removable discontinuity? So pretend that the game is that if I can give you 1 point, one point. If with that 1 point you can, again, forgive the sloppy language, if with 1 point, if you can fill in the value and turn a graph that previously was not continuous to a graph that is continuous, right? So in other words, I can't draw this without lifting my stylus, but if I were to fill in my hole, right? If I gave you 1 point that you could use to fill in a hole, well, if I could fill in this hole, then I would now be able to draw it without lifting my marker, right? Without lifting my stylus. So that is what we mean by removable discontinuity. F can be made continuous by defining or redefining a single point. Now, what if, let's take the following. What if the graph looked like this instead? What if instead of being a hole at C, what if there was a vertical asymptote? And now the graph looked something like this. Okay, so this would be a non-removable type of discontinuity. Because don't you agree with me that it's not like you can just plug in a single point here and make your graph continuous, right? So removable, non-removable, two types of discontinuity at a point. That's what we're interested in. So now, the good news is the properties of continuity allow for, scalar multiplication, products, quotients, sums, differences. You can read through the theorem on your own time. What I'm interested in is I want to discuss, I'll write it, the continuity of each function. In other words, I want to be able to make a statement of when this graph is continuous. Okay, so looking at the function 1 over x, let's you and I agree that this graph is everywhere continuous, okay, except at one x value, right? X cannot be 0. So let me make a statement here. So I would say that F is, now I'm going to put CONT, but I mean continuous. F is continuous from, well, let's write it. It's continuous from negative infinity all the way to 0, but we can't include 0. It's also continuous from 0 all the way to positive infinity. Now, in mathematics, the way we have two statements, and just like in everyday language, you use words like and or in order to join these statements, and we want to join these, and we join these with the following symbol, right, which means union. So this is where the graph is continuous. It is not continuous at 0. Let me pose the question to you. when x equals 0, that's a point of discontinuity. Is that removable or non-removable? That's non-removable, right? Because it is a vertical asymptotes. Okay, so the next function, we want to know when is it continuous. So in this case, x squared minus 1 over x minus 1. Let me show you something a little, even in higher maths, I still see little silly mistakes. So a student might notice that they can rewrite that numerator as x minus 1 times x plus 1 divided by x minus 1. And that same student might also notice that they can cancel the x minus 1's. And so they're left with x plus 1. But now, let's you and I agree that the original graph, the original function, x cannot actually equal 1, right? Because if you plug a 1 in, you're dividing by 0. But even though that this function reduces to this function, and it looks like a straight line, but even in this final version, if x can't be 1 in the beginning, it cannot be 1 here either. X, so you would have to make sure you tell your, let's say, your client that x cannot equal 1. Even though we did a little bit of algebraic manipulation and we could cancel some like factors, you cannot cancel out the fact that x cannot equal 1. So what is not shown in this graph is that when x equals 1, there should be a hole in the graph. My apologies. Yeah, so when x is equal to 1, I said it correctly, there would be a hole in this graph at x equals 1. So let me ask the same question. So how would you discuss the continuity of that function? Well, just like the previous problem, where we would say that f is continuous from, I'm writing too small here. So f is continuous from, and let's go ahead and state it. So aside from that hole in the graph, it's everywhere else, it's continuous from negative infinity all the way to 1, not including 1, union from 1 to infinity. All right, so there's a point of discontinuity at 1. X cannot equal 1. Is that removable or non-removable? Come on, say it. Say it out loud. There's no one listening. Right, that is a removable discontinuity because you could, for lack of a better word, you could fill in the hole, right, by redefining a single point. And that would, so this would be a removable discontinuity. Last one, the graph of y equals sine of x. What is the continuity? Well, don't you agree that, so obviously what goes into sine is the only thing that sine understands is angles, right? So the only thing that you can plug into a sine function is an angle. But the good news is with sine, you can plug in any angle you want. Pi, 2 pi, 4 pi, 8 pi, it doesn't matter because this graph just continues. So there are no restrictions. You could draw the sine curve without ever lifting your pen because it's everywhere continuous. It's continuous from negative infinity to positive infinity. Okay, so in the next example, what we want to do is we've already discussed some properties of continuity, and there's a theorem that I'm actually going to punt on for a little bit, but it'll come back. I'm going to bring it back when I need it in chapter 3. And that's where we'll formalize it. But for right now, notice that the questions are very similar. It's describe the interval on which each function is continuous. So let's start with tan of x. Now, so I'm providing the graph of tangent of x for you. And you're noticing, or at least what you should be noticing, is there is a lot of vertical asymptotes. Right? So clearly there is a lot of points of discontinuity. But let me rephrase that. Let's just start with just a tan of x, say from 0 to 2 pi. So how do we think about this? Well, let's start with the idea that tan of x is again just sine of x over cosine of x. Right? So tangent is just the ratio of sine and cosine. And let you and I agree that when it comes to a fraction, the only thing that we need to worry about is when we're dividing by 0. So the real question is, what angles would cause cosine of that angle to be 0? Because that's a problem when it comes to tangent. Well, clearly x cannot equal pi over 2. I don't know, I said pi over 2 and wrote pi over 9. It must be getting late. So clearly x cannot equal pi over 2, right? Because cosine of pi over 2 is 0. So you'd be dividing by 0. But furthermore, x can't equal 3 pi over 2 either. Cosine of 3 pi over 2 would also be division by 0. In fact, in multiples here, right, we have all of these multiples. So we can say that in this case, we'll just state what x cannot be to answer part A. So in this case, x cannot equal any angle of the multiple pi over 2 plus n pi. So in this case, n would just represent whole numbers, or actually, my apologies, n would just represent integers, so negatives or positives or 0. So if you plugged in 4 for n, you would get an angle that would cause cosine of that angle to be 0. So you would get a vertical asymptote. So I know we were asked about the continuity. We listed the point of where x cannot be. So if you wanted to list, you would have a whole lot of intervals that you would have to list if you wanted to list the continuity of this function. Okay, so I think that's enough for the first video, and we'll come back. I'll finish 1.4. We're getting close to the end. We'll see you then.